Hello, we're going to talk about polar form of the reciprocal of a complex number. So let's assume that we have some complex number z is equal to r cis of theta, right? Where the complex number is not equal to 0. And then we have its reciprocal, let's let it equal 1 over z, is a times the cis of some other angle alpha, right? So, well, we know that if we take z times its reciprocal, right, it should be equal to 1, right? So if that is the case, then we know that what is z equal to? Well, that's equal to r cis of theta times our reciprocal is just, we've let it equal cis of a cis of alpha, but that's got to be equal to 1. So now we know how to multiply reciprocal identities, so we know we got r times a cis, and we know that we add these two angles together when we're multiplying, and that has to be equal to 1. Now this gives us some information. Well, first off, I know that well over here, how can I represent this number 1 as a complex number in polar form? Well, if it's just going to be equal to 1, that's the same as cis of 0 degrees, right? Because at 0 degrees, right, it's just going to be at that point 1 right there. So this is equivalent, right? And then we can match up equivalencies here. So I know that, well, first I know that r times a is equal to 1, right? And then I know that my a of my reciprocal entity is 1 over r, right? But also I know that my angles theta plus alpha has to be equal to 0, or better yet, for my reciprocal identity, it's going to be alpha is equal to negative theta plus a 2k pi as it gets wrapped around, right? So those are my two identities right there. And that gives us a few things, right? Well, what does that mean? That means, well, what if I were to take some complex, if I let, this is, if I take some z, well, let's say if I take z of 1 over z of 2, right? That's the same as taking z of 1 times 1 over z of 2, right? Good. Well, what this means is I can just, if I let z of 1 be, let's say, r1 cis theta 1, and z of 2 is r2 cis theta 2, then I know that when I multiply them, I can just, it's the same as taking my r of 1 times 1 over r, right? So I'd have r1 over r2, and then the angles are going to be the opposites of each other, so I'm going to have cis. It's going to be theta 1 minus theta 2. Good. And that's my identity for that one, right? And then same applies for Euler's formula, right? So I know that when I divide them, I can apply this property, but I can also use in the same thing if I have a complex number in Euler form, e to the theta I, right? That's going to be the same as 1 over r e to the negative theta I, right? And if I take two Euler's formulas, let's say r1 e theta I over r2 e, what's it, theta 1, and then theta 2I, well, that's the same as r1 over r2, and this is e I times theta 1 minus theta 2. So you always, when you're dividing, you're always subtracting. You divide the moduluses, but the arguments, you just subtract them, right? But you make sure you subtract the top minus the bottom, and there you go. So let's go ahead and see an example using this. Let's say it says find the polar term of z of 1 divided by z of 2 in both a and b. So the first one, I go z of 1 divided by z of 2, well, I'd be 6 divided by 2, which is 3, and then I'll have cis. And what's 75 minus 20? Well, that's going to be 55 degrees. Real simple like that. So that's it. Now, this one up here, z of 1 over z of 2, right? 8 divided by 4 is just 2. And then I'd have to subtract these. 5 pi over 7 minus pi over 3. Since it's z1 over z of 2, I can find a common denominator here and here. And this would be 15 minus 7, and that's going to come out to 8. So it'd be CIS of 8 pi. 7 times 3 is 21. So there we go. And that's all you have to do for division. Thanks, guys.